So I've written my master's thesis on different replication solutions, and so I've compared them, tried to understand some or most of them, and I've benchmarked a few of them, which is what my slides are about. I guess I can share the link to the slides once more, so you can just look at the slides on your own for now if you want to. And these slides show benchmarks for in-core streaming replication, PG logical, in-core logical, and Postgres Pro multi-master, which is certainly an interesting replication system. By the way, these terms, in-core streaming, in-core logical, and PG logical, they are mostly courtesy of my friend or colleague Nick, who's also one of the Germans, whom you might have seen at conferences. A very, very large guy, and he proofread some of actually most of my thesis, and suggested to use these in-core streaming, in-core logical terms to distinguish it from the other solutions that are available. Because just saying PostgreSQL logical replication is not too clear if I'm now talking about PG logical or about the one built into PostgreSQL core. Well, and during my benchmarking, the benchmarking was relatively simple. I was provided with a bunch of virtual machines from my university, but I could only specify 8 CPU cores at max for those. And I ran pgbench in first just using the regular TPCB mode, and then using a different benchmark, which I just call the custom benchmark, because I wrote a little custom benchmark script where each transaction did was insert a single row into a single table, comparing that to the TPCB bench, which does 5 different operations in each transaction. And that just means that all the transactions are much shorter, and in my mind, that would put more stress on the replication systems. And what I observed was that both the logical replication built into the core, in-core logical, and PG logical suffer from very high CPU contention, because the wall sender, the output plugin, just has to fight all of the backends for CPU resources. Of course, Linux, the kernel, doesn't know anything about that. The wall sender process may be of higher interest, should receive more should receive more CPU time, should be more often scheduled. And I guess if there are any questions now, you could ask them, and I'll try to, in the meantime, rejoin from my other computer, where hopefully I could then share my screen if that's helpful to anybody. I've already done the introduction verbally. These are some of the settings that I used. So obviously this is not with very many clients, and the scale is also not that large, but I think that pretty much highlights that these issues can already occur at very small loads. So this is a look at the transaction log rate for the primary and the replica. And for in-core streaming replication, which is the regular binary streaming replication in Postgres, they are essentially superimposed on each other. And the replay lag, as observed from pgstat replication, is very low across the whole benchmark. So after 180 seconds, the benchmark ends. The wall rate drops almost at the same time on both the primary and the replica, and so does the replay lag, obviously. And if we are now looking at in-core logical replication, the logical replication mechanism derived from PGLogical and built into PostgreSQL itself, we now see first off a very varying and lower transaction log rate at the replica, indicated in the well, I guess you see my mouse pointer. In the upper diagram, the dotted line is for the replica. And over the course of the benchmark, the replay lag grows and grows and grows, right until the end of the benchmark, at which time the transaction log rate at the replica shoots up, and the replica is now busy applying all the changes that were accumulated in the meantime, because something was not keeping up. And this is very similar. There's very similar behavior that can be observed for PGLogical. So this is a common issue for the logical replication systems, it seems. And this means in this case, after 180 seconds of benchmark, there is at least a minute spent just catching up for the replica. And the replay lag here reaches over 600 megabytes. This is just comparing all three again. Do note that there is a very different scale for these replay lag figures here for the in-core streaming and the two logical replication solutions. And this is an aggregate of those values. And then I did the same for this custom benchmark, which I mentioned earlier, which just has very short transactions. And that, I think, highlights these issues even more, because there is, I guess, there is not just contention, but transactions are so fast to be served. Now some other effects, perhaps caching in level 1 or level 2 or level 3 caches, plays a role, and so on. And there we reach more than a gigabyte, almost 2 gigabytes of so this average maximum replay lag is the average of the peaks across 5 runs. So the replay lag is really quite bad in those cases. And now I'm going to skip a few slides, because those are mainly about other effects. But here I've tried improving this upon this issue. So there was a high replication lag for the logical solutions, and upon investigation, it seemed like it was just a contention issue between the ordinary backends, the ones responsible for serving all these transactions, and the wall sender process itself, the one that is responsible for extracting all the changes from the transaction log on the publisher side. And it seems like the kernel is unable to schedule this properly, but then again, the kernel just doesn't know anything about this. And I guess this is also all right if you're just using PGLogical for migrations. Maybe then you would have some time perhaps at the end of your migration where you allow the replica to catch up the last bit or something like that. Yeah, but I tried addressing this with C groups in various different ways. So the default was all the backends, all the backends and the wall sender are in the same C group. So I think most current Linux distributions just put, for example, if Postgres is launched using systemd, then that would land in its own C group and all the processes would be in that C group without any limits at that point. And then I tried simply splitting that, so the backends are all in one C group and the wall center is in another. And then I also played around with certain CPU sets, which you can see here. I'm sort of looking at the time and wondering how much longer how much more time I should spend introducing this issue, and maybe hear what you what your thoughts are on this. We see that the average maximum replay lag then goes down considerably already for the TPCB like benchmark case. There is of course a slight dip in transactions per second served, and the average latency goes up a little bit in some of these cases, but that might be something that one would be prepared to pay for less replay lag than for the custom benchmark with the very short transactions. The trend is pretty similar for transactions per second served and average latency. Of course, if I, for example, in the default case, the backends can mostly run on all 8 CPU cores, and if I restrict them to 7 CPU cores, of course, the number of transactions per second served somehow has to go down. And interestingly, this is actually the best case where the very last CPU core is essentially unoccupied. Perhaps this helps the kernel schedule some things, or maybe some file system stuff can happen on this last core. But at least in this case, this seems to reduce the maximum replay lag. That's that. And in Leipzig 2 weeks ago, I briefly talked to Peter Eisentraut and Simon Riggs about this, and they both agreed that these are common issues that they've seen in the field, as I understood them, where the contention is just such that the apply worker does not get enough CPU time. So for the in-core streaming, the physical replication, this doesn't seem to be an issue because the number of CPU cycles required to just send out the transaction log is very low. But to extract it and annotate it perhaps and convert some data into text and so on requires much more CPU time. I guess we should write some things down. I don't know if anybody would be interested in that, but I could try my hand at that.
Oh, can you hear me?
Yes, no.
Okay, great. So that's an interesting presentation. I think what you show us is that we choose some architecture to outperform some use cases. And of course, we certainly have some issues with systems with high transaction rate. And you show us that we need some more CPU cycles for the wall sender. And of course, in this use case that you presented, you will have more issues if you have more replicas, because you will have more wall senders. And what I'm interested is to see how we can improve the wall sender in those cases. I don't know if you check profile or something like that while benchmarking. Do you?
Sorry, what was the keyword? What did I check?
The profile of the wall sender with gperf or any other tool.
Yeah, I tried looking at that. I guess I am either not knowledgeable enough or not smart enough to deduce much from that.
Yeah, it
So I
certainly
had
will
some,
be useful.
yeah.
Check that and also explore other use cases like you benchmark very simple transaction, but it will be useful if you can also check some complex queries or queries that load data. And I think we have to check some cases and see if we can improve that. Maybe we can group the work on all of those use cases. It will be certainly useful. Um, of course, there are other cases that we can explore. I think that maybe you will be interested in some work that's being done on this logical replication performance area. From the top of my head, I remember two. One of them will be presented in this conference. That's a work from Ashutosh Bapat. And there is also some work from Amit Kapila that will probably be improve logical replication.
So you're mainly thinking of improving essentially the number of cycles that the wall sender would need to get some transaction out of the door, for example.
Yeah, there could be some strategies to improve that. I don't check this specific use case. It will be interested to have some profile and check that and figure out why Postgres are using so much CPU cycles for wall sender. Maybe that's it. Maybe we have a low hanging fruit and we can improve this scenario. I don't know. I'll have to check that.
All right, thank you. Yeah, I guess my idea about C groups that doesn't work very well. I mean, what I've essentially done is tried that manually, or I did it through Ansible, where I just looked up the PID of the wall sender and then moved that into a different C group. But that breaks already when the replication connection is terminated, maybe by a small network hiccup, and then recreated, because then the wall sender process is started again, and is of course under a different PID, so it would have to be classified into that special C group once more, for example. And that's where
Yeah.
I thought maybe Postgres could do this on its own, and honestly, I've thought that in a few cases, for example, putting all the backends for a certain database user into a special C group, for example. But I guess that is a very large topic.
Yeah, I'm not sure if people will agree to add some OS specific into core, but it can certainly start a discussion. Maybe we can consider something like that. I don't know. I see two issues here from your presentation. One of them is the wall center, of course, and the other one is on the replica. That's the startup process, because you show at the end of the benchmark you have the startup process just applying the backlog, and it's kind of a hard problem because you have to figure out how to, for example, parallel apply the transactions. And I think we have some discussions in the past about this topic. I don't have a link, but you can check the mailing list. And it's also another point to improve. And it will certainly improve not only the logical replication, but also the streaming replication. I mean, the physical replication. And it would be another interesting topic to explore, in my opinion.
Yes. So what exactly do you want to speed up? What are you specifically?
The replay.
Okay.
The replay routine. So, for example, if you parallel apply the replay routine in the startup process, you can speed up that. Of course, it's a hard problem because there are some transactions that has some interdependency. So you have to make sure to not have that. But let's say you have totally separate transactions. Transactions that touch different tables, and you can parallel apply that without any issues.
Well, I wouldn't be too sure about that. There might be some intertable dependencies, foreign keys or something.
Yeah, that's
I
why I
agree that parallelizing, the simplest level of parallelizing is just having multiple subscribers and publishers, other way around, publishers and subscribers for each table in PGBench, for example. And that would parallelize things. I'm not sure if out of the box right now, I don't think it would improve anything very much, because the battle for CPU resources is still going on, and in total, all the same transactions have to be somehow moved out. And for these cases that I've tested, the logical apply worker, the replay worker, was mostly at maybe 70 or 80% on a single CPU core, so not at least that was not at its limit, but I also tested this a little bit on a larger system with 32 cores, where I was easily able to saturate the replay worker. Too many things that I've tested.
Yeah, I think you have one case, and there are so many things to look at this specific use case.
Yeah. So I'm also trying to write some things down. Should I copy that somewhere if anybody has any other?
I think you have to add to the wiki, maybe create a wiki page and edit this link here.
Any other thoughts from maybe from the rest? Has anybody seen similar issues? Maybe in production, because, well, yeah, I have to say this. I really only have, let's say, this academic experience with logical replication, and haven't run any logical replication in production anywhere.
That's one of the talks I was talking about.
Where
that
is
can
it?
improve some scenarios.
Oh, okay. Yeah, I was also interested in that.
Okay, great.
But I can't time travel. I don't know yet what will be in there. And yeah, I have to admit I haven't looked into the mailing lists, the hackers mailing lists recently, to see if anybody is currently working on improving things. Okay, so you...
Yeah, we have a lot of proposals. Not in this particular area, but the logical replication in general. It's a hot topic.
So, okay, I'm logged. Your suggestion is to simply create a new page on the wiki?
Yeah, I'm not sure. That's a good question. Let me check the previous conference
Maybe
link.
that's something.
Okay.
Any ideas?
I think you can use the same page. I'm checking this. I'm checking this wiki page, and they put everything in the same page. No need to add a separate page.
Okay. Does this wiki support sort of parallel?
I think so.
Well, I guess there's no other way but to try. Does anybody have any ideas that would work platform independent? But I mean, everybody is fighting for CPU time, so that there is really nothing like indicating, hey, I need more CPU time right now. Maybe, I mean, niceness should be something that at least the BSD systems support. And macOS, I don't know if Windows has something similar to niceness.
Yeah, I don't think so. I think your best bet is to use something like that, or even use a connection pooling solution. So you
Just to limit
provide
the load.
some, yeah, you provide some CPU space for the wall sender.
Hmm. By the way, may I ask you how to pronounce your name? First name.
It could be like German, Euler. That's how some of my EDB colleagues called me.
Okay.
But in Portuguese is Euler.
Euler.
But
Okay.
you can call me Euler, no problem.
Okay. I think I would do a better job of pronouncing your family name.
Yeah, Taveira.
Yeah.
It's a Portuguese surname.
So I mean, Windows has priorities instead of niceness. No. Well, and I know that Windows has something that's similar to, you can just pin threads or processes to specific CPU cores in Windows.
Yeah, I'm not a Windows guy, so
Yeah.
I can't provide you any feedback.
So if we had to think of some things that should be done to further this discussion, would be to look at if there are any obvious optimizations to be done in
And wall sender.
Wall sender.
And maybe start a discussion if we really need an in-car solution for this problem.
Mm-hmm.
I will probably say no for some of the options we have, like you mentioned, the C group, and also the connection pooling solution.
Yeah.
So we have workarounds, let's say that.
Yeah.
And of course, if we don't have a solution, we could probably have an in-core solution, like say, for example, for the case of huge pages that was included into PostgreScore. But we have some alternatives, and I'm not sure people will say, hey, let's include this in core. But of course, you can start a discussion and see what other people have an opinion about that.
I mean, you could argue that even if you only go around maybe once a minute to see if there are any new wall sender processes that would have to be moved into a different C group, for example, that would probably cover most cases where the connection breaks up and then a new wall sender is spawned upon reconnection.
That's a really good question, because the way that we have wall sender, we don't have control. Maybe we have to expose this information in a way that the solution you implement can know the PID at the time you start a new wall sender process?
Well,
For
I was
example,
mainly thinking of a hack job with a small bash script that is running permanently, waking up every 60 seconds, maybe just looking at the process names. If there are any ones that are named wall sender, then it could check if they are already in the specific C group and move them there. That would be a workaround that doesn't need any patching of the core.
yeah, fair enough. But if you have, for example, any network issues, I don't know, maybe you don't have it, but you will have to at least 60 seconds time frame without applying that, and maybe it's not a good solution for your problem because you will have a huge replay lag in that minute. Maybe you have to tune your script to use a small time.
Yeah, I mean, I just haven't tested this. Maybe I don't know. Maybe it takes lots of CPU time to check all the C groups or move something to a C group, or maybe it's just very cheap to do so. I mean, in theory, you could just touch a single file, yeah, to move some.
I'm not sure Dan can grant some privileges.
Yeah, it was just a shot in the dark.
Okay, yeah. There are some group of people that can grant you access.
I could write to the mailing list. Hop on the
If you
IRC
prefer,
channel.
You can share it with me, and I can add it after my lunch.
Yeah, sure. Hold on, let me somewhere.
Can share it with me. I added my email address in the chat. And you can certainly ask for an wiki account on the PGSQL-www mailing list.
Yeah.
Just send an email. Hey, I have this account. I want to edit the week for the conference or something like that. And someone else will edit your account.
Yeah, so what do we go back to the first room for now? What's the...
I think it's lunchtime. So
yeah.
We are back in 1 hour.
All right. Yeah, I'll ask if there is anybody around. And otherwise I'll send you an email with the what I've written down. All right.
Okay,
Anything
let's
else?
wrap up from here.
Yeah.
No. Bye.
All right. Thank you for your input. I appreciate it. Let's keep improving the logical replication.
Yeah. Have a lot of places to improve. We have a lot of places to improve in the logical replication path. And of course, there is a lot of ideas, and we can certainly consider some approaches, and maybe it's good just to check if there is a popular use case that we can improve, and let's do it.